All right, hello everyone. Welcome back to Theory Track at ACM AI. So this week, because of the weather, we are doing this online, obviously, and I know a lot of y'all have CS32 midterms, so sincerely good luck with that. It's actually happening at this very moment, so hope it went well when you're watching this recording back. But today, what we're talking about is modern CNN architectures and RNNs, and specifically, modern CNN architectures. What we're talking about is how deep learning really got its name and how it really became possible, because there are actually some challenges that prevented people from just making a lot of different layers for CNN and going deeper and deeper and deeper. There was challenges in the way that prevented us from just blowing up the number of layers, right? Like, for example, CNNs were created back in 1998, but using deep learning for CNNs really only became a thing in 2012. There's a reason why there's a huge gap there, and we're going to talk about that today. And of course, at the end, we're also going to talk about recurrent neural networks, which is a very important thing for us to be able to deal with sequential data, and something really important for projects track when you eventually will have to do in the next quarter. So without further ado, let's get started. Again, you can find the slides in this link over here. I'll give you all 5 seconds. Cool. Also, one quick announcement. This Saturday, we have a reading group from Will Zhou, who was one of the ACM officers. He does research on some reinforcement learning stuff and also some transformer stuff. And we're going to look at mechanistic interoperability for transformers. Specifically, it is about how we can look at the different neurons and dissecting these transformers to see how they really work and really see how different neurons correspond to different things in transformers, which is a very interesting thing. And transformers are the things that power modern large language models like ChatGPT. And if you want, we're going to go through transformers in this reading group, but if you want a more comprehensive overview of transformers and we'll add to it, next theory track workshop will be a really great place, because that's exactly what we're going to talk about. Again, more of that later. Again, here's the theory track roadmap for W24. We're currently here. Yeah, again, if there's anything you want us to cover, just let us know. So, and this is today's overview. Speaking of overview, let's start with the first thing, which is a quick review. So now y'all are probably familiar with feed-forward neural networks. Specifically, we call it feed-forward because you start from the input, you transform the input with some mathematical operations like, matrix multiplications or convolutions or, nonlinearity, stuff like that, and you get to some sort of output, right? That's called a feed-forward neural network, and that's what we have been talking about so far for both just normal neural networks and also convolutional neural networks. And with these, we have talked about loss functions. Specifically, we have talked about maximum likelihood estimation, which is how you can take the outputs of a classification problem and then actually calculate a loss for that. We have talked about gradient descent, which is how we can actually optimize and nudge the weights and biases of those neural networks so that we find the best parameters to lower the loss. And we also last time also talked about backpropagation, which is how you actually calculate the gradient for this task. And we also talked about convolutions, this convolutional operation last time, which is really, we call it dragging and adding, because we're dragging kind of this filter through the image. And as each time we're kind of dragging the filter through the image, we're taking a dot product, or basically a pairwise multiplication of the filter and the image itself. And we are adding it together, and that will be a sort of a pixel in our output layer. This is done over multiple channels, and it's kind of like a dense connection over each channel. And importantly, the filters specifically are the things we're gradient descending to learn, that we're optimizing to learn. And pooling layers specifically help us, like between each intermediate layer of the convolutional layers, we may use pooling or we use strides to also just reduce the feature size. And the reason for doing so is so that we also talked about this last time, but so that features in the deeper layers are able to see more of the entire image. Because if you think about it, a single convolutional feature is only able to see a 3x3 patch of the original image. But as we, keep downsampling the layers bit by bits, what we're able to do is that because we're downsampling the feature space, as we get to really deep layers, it is able to effectively see the entire image, which is how we're able to even make CNNs work in the first place. So to kind of talk about how we got to deep learning with convolutional neural networks today, I'm going to take a little bit of a trip down memory lane with a short history of convolutional neural networks. So back in 1998, we had something called the LeNet, which came from the very, very famous machine learning scientist, Young LeCun, who is one of the three, I believe, 2018 recipients of the Turing Award, which is kind of like the Nobel Prize for computer science. And him, along with two other co-authors, kind of got the highest award um, for the sort of establishing the foundations of modern machine learning as we know it. And it's very important because it was invented or proposed back in 1998, where it pioneers the basic architecture of a convolutional neural network. You know, he proposed convolutions and pooling, and specifically, this was a project actually done for the USPS, if I remember correctly. Because the USPS had a really big problem, which is, hey, we have customers sending in all these packages with handwritten labels, right? Handwritten addresses. How can we put that into a computer system efficiently so when we send this package off, it knows how to like sort the packages, you know, on these conveyor belts into the correct trucks, into the correct larger packages, into the correct even like, you know, large shipping containers. How can we effectively sort them? Because to do that, we need to be able to do something called optical character recognition, which is look at our sort of shipping label and be able to convert that into actual, you know, computerized ASCII letters, right, and numbers. Before that, what they will do is you will have thousands of these things. Like Tom Scott has a really great video on this, but you will have thousands of these stations around the US where people will sit there and all their entire job will just be looking at a picture of a label or a scan of a label and typing in the address to that label. What LeNet managed to do is basically automate that process so that today there's only one such facility remaining for extremely difficult optical character recognition, really extremely messy labels that machines fail at reading. Right. So that was really, really influential back in 1998. But the thing is, you may realize the next influential thing about convolutional neural networks came in 2012 with AlexNet. What happened in the middle? Why is there this 14-year gap, right? Machine learning is moving so fast today. Why did it take us this long? So I want to talk about what happened in around 2010, which is something called ImageNet. So ImageNet is a classification challenge. So if you have thought about, you know, like for those of you who are in applied track, we looked at MNIST and we look at CypherTim. ImageNet is basically a really huge version of it. It's a huge classification challenge that started in 2010. There are 1 million training set images, 50,000 validation set images, and 150 test case set images. Again, like basically, the organizers will release to the people all images from all three sets, but they will not release the labels for the test sets. And basically, what you have to do is you will train your model on the training set images. You're allowed to test your model, play around to see how its accuracy does on the validation set images. And then you just have to send in a massive .txt file containing the label predictions for the test set images. And then because you're not given the labels, you can't cheat, obviously, right? And 150 is way too many for humans to manually label them. And then they basically run through your TXT and see who does the best. And this is how they would able to properly have a competition on this. And it popularized deep learning as it worked so well. Like specifically here, AlexNet, which is the very first CNN network that utilized deep learning, you look at how much of a drop in the classification top 5 error is. And top 5 error is basically whenever a model outputs what it thinks the classification result should be, remember it's a probability distribution, right? So in this case, they basically say, look at the top 5 probability distributions. If any of them are in the correct ground truth, or if any of them are correct, then we count that as correct. Because a lot of times some of these labels, when there's 1,000 labels, you know, things can get confusing or like things can get ambiguous, right? Like one of the examples is you may have a picture of like a dog in the foreground, dog in the background and the flowers in the foreground. And the model may be like, oh, that's a dog, but then the correct label is actually flowers. So, you know, like we can have ambiguous images like that in the data set. Anyway, so basically 2020, 2011, these are not deep learning papers, right? These are papers that are very much, they're shallow learning papers. They're papers with very few layers. And they use a lot of data engineering and a lot of basically kind of like elbow grease to get even accuracy as good as this. And then basically AlexNet came out and just destroyed everyone. So to give you, and here's some examples on ImageNet, right? It's 224 by 224 in resolution. So it's actually pretty big as well. Okay, so why is there such a big gap between 1998 and 2012? The short answer is gradient vanishing. right? So the deeper the neural network, the smaller the values gradients will be, because remember, the way we do backpropagation is through something called the chain rule, right? And you basically have a bunch of matrix multiplication where you start from the output and you slowly go back to the input. The more matrices there are, the more of these multiplications we have to do. And sorry, the deeper the layers, the more of these multiplications we have to do, right? And the problem with this is around this time, people were using sigmoid activation functions, like for the nonlinearities, which looks something like this. If you were to take the derivative of this function, it will look something like a curve that goes up. I don't know if you can see my cursor, but it will basically be a curve that goes up, and it will kind of max out at 0.25. So you essentially have gradients that are affected by that, where you're multiplied by this 0.25 number every single time. And if you multiply 0.25 a bunch of times, it just goes to 0, right? It's a geometric series. And even with something like tan H, or like, hyperbolic tangent, which basically is not going between 0 and 1, it goes between -1 and 1, where its maximum derivative is 1. Because it kind of tapers off at the edges, because like what we call the saturation of the neurons, because as the raw values of your outputs become very big, because they get kind of taper off to between some fixed 0 and 1, the gradients become very small for those values. And we're basically getting gradients that are so small that we can't train on neural networks anymore. So now you may be wondering, okay, this was before we learned about rate loop, right? So what did people do before deep learning? So here's an example of what people did before deep learning. This is slides I stole from Professor Bolejo's CS188 class, which is offered every winter. But basically, one of the things that they did was something called back of words, which is basically you extract random patches from your input images, you cluster these patches to form what are basically called code books of visual words, basically the most representative patches. And I kid you not, you basically kind of slide these patches through the image to be like, how many of these patches, or like how representative is this patch in the image? You figure out the kind of distribution of that for your bag of words, and then you train a neural network on that. It kind of feels like convolutional neural networks, doesn't it? But instead, you're kind of using this a lot more jank and elbow greasy methods to figure out where your patches or your filters should be. And like, here's a pipeline for that, where you have an input image, you do this sort of feature extraction, and you're basically saying, for like top building street versus suburb, they have kind of different distributions of what these patches would be, right? And this is actually what the winner of the 2011 ImageNet Challenge did. They did this sort of, feature extraction. They did some compression crap, and they did this SVM learning, which is just, SVM is just a sort of fancy, it's fancy logistical regression, right? It's a fancy one layer large neural network that does some other things with this loss, but it's basically that. And then, there's some fusion of SIFT and color system. But the point is, this is what computer vision looked like. This is what classification looked like. And it looked okay, but the issue is, we have, what we're currently doing is things in the top, right? We're doing this sort of feature extraction, where we are given these features, and then we're trying to learn those features, and the training only stops at the features themselves. However, if you remember from training neural networks, we want to somehow train the feature extraction process as well. We don't want the feature extraction process to be something that we define, right? Because we never define the best things. So the bottom approach in this case seems a lot more flexible and scalable. So how can we just train a deep CNN and avoid the, avoid the gradient vanishing issue? The answer was proposed in AlexNet back in 2012. The ILSVRC stands for ImageNet's Large Scale Visual Recognition Challenge, which is the full name for the ImageNet Challenge. So AlexNet is a CNN designed by Alex Krzyzewski, and also the second author of that paper is Elia, who is actually one of the chief scientists at OpenAI. And if you guys recall the whole Sam Altman fiasco, he was one of the main people who suggested to fire Sam Altman. That was the whole thing. Yeah, he was one of the original authors of one of the most influential machine learning papers. Man knows his stuff. Anyway, so basically it is a paper titled Image Classification with Deep Convolutional Neural Networks, and it's one of the most influential publications in ML and pioneering deep CNN. You can see the cited by number here, 124,000 citations to today. And it won the 2012 ImageNet large scale. It won the challenge by 10% compared to the second place, because no other paper at this point was using deep learning, right? So the structure of it looked like this, right? You started with a convolution, and then you have a max pooling, you have a normalization layer, and this normalization layer isn't batch normalization, which we'll get into. It was some sort of like other normalization layer that didn't work as well, but it did help with gradient vanishing. You have convolutions, max pooling, normalization, convolution, 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 and then at the end you have some fully connected layers, right? And if, for those of you, again, for those of you who are in applied track, this may look very familiar, right? If you were looking at how we built, CNN networks, like Liu was going through it last Wednesday, this looks really similar. It's to what a CNN network kind of looks like today. And there's a reason for this, because this works so well. We keep using this sort of convention of convolutions, max pooling, and then maybe non-linearity and then some sort of normalization, right? So yeah, like Luxon was basically today's default CNN architecture. And an architecture example, like to visualize it, looks something like this, right? You basically start with like a really large image with very few number of channels and kind of slowly inflate the number of channels while downsampling. And by doing so, in the earlier layers, you're essentially just kind of parsing the image for different features, whereas with the deeper layers, you're kind of looking at a really long list of global features that you're extracting. So that's kind of what's going on with AlexNet. And then you have like almost like a fully connected neural network at the very end here that just kind of takes the outputs of these convolutional layers, if they flatten it, and you just kind of go, okay, let's just classify this with our final classification output. So that was basically what AlexNet is. And I want to kind of give you guys a sense of why this is so important. So y'all use PyTorch, right, for applied track. And PyTorch is awesome. Like building this is like, when you get familiar with PyTorch, it's like at most 30 minutes in PyTorch. However, this was before PyTorch was a thing, right? PyTorch was kind of released in 2016. The equivalent from Google, TensorFlow, was released in 2015. This was 2012. And to be able to train this on a GPU, they had to write CUDA code in what is basically C++. I want you to understand how difficult that is. You have to implement backpropagation from scratch. I just wanted to let that sink in a little bit. Not in Python, in CUDA. This is exceedingly difficult. And then also, back in the days, because no one was using GPUs for machine learning, right? Deep learning wasn't really a thing yet. GPUs were for gaming. And it was like 1080p gaming back in the day. So GPUs only had like 3 to 4 gigs of VRAM on the top end. There wasn't server-grade GPUs with a crap ton of, VRAM, because no one needed that, right? And maybe besides, some 3D renderers, and animation studios back in the days. So in order to train this network, they had to split the network into 2 GPUs and then write CUDA code for that. This is not just like a feat in like machine learning. This is also a huge engineering feat. And I want to emphasize how like just influential this paper is, because it showed people, hey, it is worth it to not just do deep learning, but make things that make deep learning easier, like PyTorch and TensorFlow. I believe Torch around this time existed. Like Torch was basically like the C++ version of PyTorch. That existed, but again, it was only used, and it was from Facebook, now Meta, at that time. But again, like we did not have the convenience of just being able to define your layers in PyTorch and have it just work and have it just do backpropagation for you. So moving, we're going to fast forward by 2 years, because 2013 was basically like AlexNet, but they do a little bit more algo stuff. So this is GoogLeNet, or GoogLeNet, because they are paying homage to the to LeNet. You will see sometimes the L here is written with uppercase. And they produced something called the Inception module. Why call it the Inception module? Because Inception was a really popular movie released in the 2010s. So it is the winner of the 2014 ImageNet challenge, and it introduces Inception modules networks, and which is kind of like a network inside a network. And the main idea is that it has parallel filters with different sizes to detect varying size features. Actually, before I move on, anyone has questions about AlexNet and why it's important, how it was built, stuff like that? Any questions before I move on? And can just go off. Oh, we have more participants now. That's awesome. Feel free to just unmute or even type something in the chat. I can check that. Okay, cool. I'm hoping the importance of AlexNet is being communicated across. Okay, so let's move on to GoogLeNet 2014. And also very importantly, GoogleNet was entirely trained on one server, on a few server-grade CPUs, which is a huge feat because GoogleNet was also much more efficient than AlexNet and had much fewer parameters than AlexNet. So basically, the question is, the size of a feature can vary from image to image, right? In this case, like in the case of a picture of a dog, for example, the size of the dog is very different in each image. But we want our model to be able to recognize, hey, that is a dog from all of them, right? So how do we address this problem? And the idea is by using this thing called an inception module, which is basically doing convolutions in parallel. Specifically, let's say this is just a layer in inception. The naive version is that basically you split the inputs and you just pass one of them into a 1x1 convolution, a 3x3 convolution, a 5x5 convolution, and then also a max pooling layer to kind of carry some features on, and then you just kind of concatenate them together by the end, which seems simple enough, right? You're able to look at the input image in different sizes of filters. And this also had the really important thing of doing dimensionality reduction. And the reason is because AlexNet, if you actually look at the paper, they used convolution features like filter sizes up to 11 by 11, which is fine. It's still much smaller than if you were to use fully connected neural networks. However, larger kernels are actually still very expensive because if you think about it, a kernel that's 5 by 5 is 25, right? 5 by 5 is 25. And a kernel that's 3 by 3 is just 9, which is like about 1/3 the size of a 5 by 5 filter. Filter sizes grow in n squared, right? And usually we want to use odd filter sizes because then there is a very easy mathematical sort of center to that filter. You don't have to, but it just makes the math slightly easier when you're trying to figure out what filter sizes you should use and what padding you should use when you're actually coding in practice, right? And the idea is that larger kernels are actually really inefficient. Like they actually still take up a lot of parameters. Like for example, if the previous layer outputs a volume with depth 256 and the current layer has 5 by 5 with 256 kernels, then there are 5 by 5 by 256 by 256 total weights, which is again less than the amount you will be dealing with if you're just using a naive fully connected neural network, but that's still a lot. And what the 1x1 convolutions are doing is specifically a 1x1 convolution kernel maps one column to one voxel of the output. So you're doing convolutions, but you're kind of just dragging this one pixel thing over the image. So instead of doing, say, 256 depth to 256 5 by 5 kernel, which has this many weights, we can do a 256 depth to a 64 1x1 kernel, and then back to a 256. So the input and output dimensions are the same, but you have much fewer weights. And necessarily, you may think, oh, but it's not going to perform worse because we're kind of compressing this information down to a much smaller number of channels and inflating it back to 256 channels, right? Are we losing information? And the answer is yes. Like technically, you will be losing information. But the key is with machine learning, you're training the network and you're training them separately. You're not training them with the same gradients, right? They don't even have the same gradients. And because of that, even because you have this limitation of like, oh, I'm compressing this information, I'm inflating it back, the network will learn the proper weights and biases to kind of combat that, to kind of be like, okay, how can I extract the best information so that I can do this compression and like, inflating it back again. So we're actually able to save a lot of weights. So here is, Inception v2, which is them saying here is like our final version of the Inception modules, which is, with 1x1 convolutions. And specifically, something I also want to mention is the previous layer is 256, right? We're splitting up 256 into 128, 64, 64, and then we're splitting this into 4 equal parts of input channels of 64 dimensions each. And that also reduces the number of parameters really well because instead of doing 256 times 256 in the channel dimension, you're instead doing like 64 times 64 and then doing that 4 times. And mathematically speaking, that is much better because 256 by 256 is like 16 times or like, sorry, at least 16 times of what 64 by 64 would be. And then there's 4 of 64 by 64. So basically, the number of ones we're splitting out grows linearly. But if we don't do that, it grows by n squared. Right. Again, like this is something you have to like really kind of sit there and just like stare at this and be like, and convince yourself, yes, this is beneficial because it reduces the total number of parameters, but it does. And that's how we're able to really reduce the total number of parameters and be much more efficient with training. So that's basically what inception is. And one more thing that that inception does that I actually kind of want to show you is let's go to the inception paper. So yeah, going deeper with convolutions. Again, the question is about going deeper and deeper and deeper. Another thing that the inception paper, again, you can see it's from Google, the inception paper did is it basically said, okay, we have these inception models, right? They're awesome. However, we're going deeper with these layers, and we're still running into a lot of gradient vanishing issues because I forgot to mention this, but what AlexNet did is AlexNet also started using ReLU, right? If you remember what ReLU looked like, I think we're missing like a slide or two. If you remember what ReLU looked like, it's just a flat line and then it's just kind of like an x equals y, right? The gradient for that is much nicer because you have 0 for all the gradient is 0 for all negative values and the gradient is 1 for all positive values, right? So the gradient is much closer to kind of like the identity, right? If you multiply a bunch of these together, it's going to converge to 0 much more slowly. However, you're still going to converge to 0 because you're chopping off the gradients for all the negative activations. So what GoogLeNet says we can do with trying to reduce this sort of gradient vanishing problem is by using something called an auxiliary loss. So this is very long, right? This is basically their entire network architecture. They really populated an entire letter paper with this. But I'm going to zoom out a little bit and show you what's going on. What you can see here is on the top, we have all these layers, but around like layer 11, you can see in the middle, it goes out to a softmax layer, like specifically here, right? It kind of splits off and it kind of just goes out to the first softmax and it does it again. And then it does it again at the very end. Also, sorry, this is the input and they reverse the order. But yeah, like here it goes out to a softmax and then it goes out to a softmax. And at the very end, it goes out to the third softmax. The idea of what they're doing is they're saying, okay, we pass in an input. We're doing classification in 3 places. We're taking the output of this layer, and putting it into some fully connected networks, and then then looking at the output of the final layer. And we're doing classification on all 3 of them. We're using all 3 of them to train our model. And the important thing is this. When we first initialize our model, all of this is just like random noise, right? The gradients in the lower layers will be really bad because the gradients will usually kind of converge to really low values. However, the gradients for these upper values, the gradients, and basically the problem becomes the gradients for these layers down below, like the layers that's closer to our final output, will be nice and large because they are it's very few layers compared to what the actual output is. However, the gradients for the input layers will be extremely small because when we're back propagating from here all the way back down to here, we have done matrix multiplication so many times that we have once again made our gradients go to 0. However, by doing classification here, we're inducing sort of gradient flow from here. We're inducing another gradient flow from here, which kind of, because there's so few layers here, kind of inflates the gradients a little bit more. And we're having another gradient flow here as well. So by having these 3 auxiliary losses, or these 2 auxiliary losses, what we have managed to do is kind of circumvent this gradient vanishing problem by essentially injecting more sort of classification information in the intermediate layers, so our earlier layers will have gradients that don't vanish away. Does this kind of make sense? Any questions? Can I see a thumbs up reaction if this makes sense to everyone in Zoom? Okay, cool. We have one from Saya. Okay, cool. Yeah. So basically, this is one of the ways that they have been circumventing this gradient vanishing problem, and it's pretty clever, right? Having this sort of like let's add in these intermediate layers so that the gradients don't just go to 0. And this worked pretty well. Like one of the main things is that this network is very, very small. It is much, much smaller compared to AlexNet, right? It is much smaller compared to AlexNet. And another reason for that is because AlexNet did this thing, which is it had a bunch of convolutional features at the end, right? Again, this is just a side note, but I think this is fun to talk about. It has a bunch of fully connected layers at the end. So you have 4096 times 4096, and then you have that in times 1000. That's huge. In fact, these features, the fully connected features for AlexNet, makes up 90% of the total number of parameters. Because, again, fully connected layers are so much less efficient in terms of number of parameters than convolutional features, right? So another thing that GoogleNet did is they did something called the called the global average pooling. Here, average pool, right? And what they basically did is they said, okay, our output feature at this point is 7 by 7. Instead of just 7 by 7 times, say in this case, like 512 channels, instead of flattening out that to just a huge vector for us to do these fully connected layers with, let's just take that 7 by 7 feature and just average it to be 1 pixel big. Why do we want to do this? Well, the reason is because when we're at the very end here with the 7 by 7 feature, right? What's actually happening is because we have 512 of these output feature maps, each 512, or like 512 is the number I made up, it's probably something slightly bigger than that, but like each of these channels represent a sort of intrinsic feature about the original image. So if we just average pool them, that's basically saying, oh, this feature I extracted, how much is it in the original image? And because you have compressed by average pooling them, your flattened vector is so much smaller, therefore, and they only use one fully connected layer. The fully connected layers don't actually take up that much number of parameters in the paper. And that was really cool, right? They actually show you, it's like, oh, like the fully connected layers actually don't take up anything because average pooling is you're just taking the average of each feature to make one value, right? That doesn't cost any parameters. So GoogleNet proposed a lot of really insightful innovations that made sort of the next paper that we're going to talk about, which is the most influential paper in machine learning. So it actually made it possible. Like the idea of, for example, global average pooling, which is the sort of like taking final feature and just kind of like averaging it that I was just talking about. That was also used in the next paper we're going to talk about. And also what really made a lot of these like deep convolutional networks large, but at the same time, large, but putting most of the parameters in the important parts, aka in the first few convolutional layers. And that, the thing I've been kind of foreshadowing to is something called the ResNet, which is the winner of ImageNet 2015. Liu, you are muted.
Sorry.
Yeah. Okay.
Hey, Jordan, do you want me to share my slides or wait?
Just let me know to go to the next slide.
Okay, sounds cool. So now we'll be talking about ResNet. This was the winner of the ImageNet classification award in 2015. And it is one of the most cited papers. I think it is the most cited paper in machine learning. It was a hallmark specifically because it addressed a very large problem in machine learning to that point. Before we kind of get into it, I kind of want to like emphasize that this paper and this specific architecture is sort of like the epitome of what it means, what deep learning is, right? It's neural networks that have a deep architecture rather than sort of like a horizontal architecture. They have a more vertically oriented architecture. And so, yeah.
And another thing is the thing that ResNet proposes is something that is used in literally every single neural network you'll see these days. Like the thing that they propose is called residual connection. Everything after this paper includes that. That is how influential this paper is. Almost every single architecture will have influences from this paper. And specifically, it was the winner of the 25 competition, and it was the first time that we beat human performance, right? So basically what they did is in 2014 or something like that, a bunch of grad students in Stanford got bored one week and they went, okay, we wonder what the actual human performance is like for ImageNet on humans. So they just kind of sat down and just spent a week and just like classifying images by themselves. And they realized the human performance, top high performance is around 5%, right? ResNet managed to get to 3.5-ish% in terms of error, right? We're talking about error here. 3.5% error, which was better than human performance. And the first time we actually reached that point. I'll hand it back to you.
Yep, that's a really good point, Jordan. Even if you guys look at transformers, they have residual connections too. So, GPT and so on, a lot of the fundamental ideas, some of the fundamental ideas actually came from the ResNet paper. And so to start going into that, what is the motivation? Why do we need ResNet, right? And the reason is it has to do with the problem of increasing the depth of your neural network, right? Like as you go deeper, some issues start to arise. So deeper networks generally have should perform better, right? Because you can model more complex behaviors using deeper networks. But originally, before 2015, before the ResNet paper came out, this was the opposite, right? As you go deeper and deeper and deeper, your model performance actually decreased. And so there was this sort of contradiction where we thought because these networks are deeper, they have more complex, they should have more complex prediction capabilities. The reverse actually happened, right? And this is what ResNet is trying to fight against. It's trying to make it so that deeper neural networks have higher performances, and so you can scale neural networks in that direction. And as we can see in the graph here, this is just a plain neural network. As we increase the layer, convolutional neural network, as we increase the layers, the number of layers from 20 to 56 layers, we see that the training area has actually decreased, right? And not only that, this means that the test area has also decreased. And so this is one of the things that ResNet really tried to figure out, and it did very, very successfully. And also, just a little side note here, I will show you guys an example of a ResNet architecture from scratch in PyTorch, just like a very, very, very quick demo on that to sort of give you guys a sense later on. Yeah, Jordan, you go to the next slide. So we're in too deep, right? Why would this be the case? Well, if a layer is unnecessary, suppose, for example, you have a 5-layer neural network, right? And a 5-layer neural network has a certain accuracy, right? And suppose you can, get a 10 or 15-layer neural network, right? In an ideal world, the 10 or 15 layer should have at least the same capability as your 5-layer neural network, right? Because you could just make the rest of the layers identity function and they output the exact same thing as a 5-layer network. But this doesn't happen, right? The opposite of this happens. And the reason is because neural networks can't mimic the identity mapping. They're not good at this, right? They're not good at taking an input and giving you back that input. And just to give you guys an intuition into why it is, think about, for example, you have let's say a multi-layer perceptron or just like feed-forward neural network, right? And the activations were something tricky. Let's say, for example, sigmoid, right? If you wanted to get the same input as, if you wanted to get the same output as your input, your neural network would actually have to learn the inverse of your whole neural network. You have to learn the inverse of your activations. And so as your neural network has more and more and more and more complexity, your neural network has to learn the inverse of that complexity, right? For that identity mapping to happen. And as you increase your layers, sometimes the number of activations increases drastically. And so to learn that complexity can be very challenging. Next slide. And you can, yeah.
Yeah, and another thing is in practice, we often see that the extra layers kind of just learn basically the zero function. They just kind of collapse all to just a bunch of weights that are all zeros, which is, again, you may imagine not very helpful because then all your outputs are just zeros and you have learned nothing, right? Yeah.
And to give you guys a glimpse into how the residual block works, that's the essential building block of the ResNet architecture. What we specifically do is we take our input of, let's say you have a specific layer in the middle of your architecture, and we add that input to the output of our layer. So rather than just going through the whole neural network, we take our input and we add it to the output of that layer. And that's what we call a skip residual connection. And that's effectively what ResNet introduced, right? We take our input and we add it to our layer. And you guys might be wondering, why does this work? Why is this effective, right? If you could go back to the previous slide. So yeah, specifically, I want to highlight two important reasons. And on the next slide, we'll explain what the difference is, but I just want to highlight two important reasons. Number one, your network doesn't, before we introduced residual connections, your network had to sort of transform your input to the layer to the output, right? That's what it does. It takes an input and it transforms it to the output. And it has to learn that transformation, which can be quite complex, right? But now all your network has to do is learn the residual part of that connection, meaning the difference between your ideal output and your input, which can be much more simple in many circumstances, right? So we actually simplify our problem when we add an identity mapping. In addition to that, another big problem that the residual connection solves is optimization, right? It optimizes gradient descent. One of the biggest issues that you have when working with large models is the issue of the vanishing gradient problem, right? Because if you guys remember last time when we were discussing this, we talked about how as you backpropagate through your network, what you're just effectively doing the chain rule, right? You're multiplying your gradients as you go back through your layers, right? And this leads to sometimes a drastic decrease in your gradients for the earlier layers. So these earlier layers, they can be hard to change and update, right? But when you have a residual connection, there's gradient flow not only through your main, sort of main line through that block, but also between your output and your input, right? So it allows the gradients to flow more easily across your neural network, and it leads to actually better complexity for your machine learning neural network. And so those are two important reasons I want you guys to sort of have in mind. Next slide, Jordan. Yep. So what in the world is a skiv connection? So specifically, just to give you guys a glimpse, like a specific, like just an example. On the left, we have a regular neural network. So we have this regular vanilla neural network. We have an input, hidden layer to an output layer, right? Nothing special about this. And on the right-hand side, we have our residual connection, right? Where we have two hidden layers. And on our second hidden layer, what we add is the input layer. And then our hidden layer 2 is our hidden layer, times, our hidden layer times our weight, plus our bias, plus our input layer function. That's what our hidden layer 2 is going to be. So we add our input layer to the activations of the hidden layer 1. So that's the residual connection part, right? That's where our input comes in. And so this way, we don't actually have to learn that the transformation between our input and our hidden layer 2. We just have to learn the residual part, the difference. And this leads to a decrease in complexity. Next layer. Yep. And if the weights go to 0, then the layer becomes the identity mapping, right? So effectively, this means that you guys remember the previous problem we had, where we had a bunch of different layers. And as we stack these layers up, at least they should be performing as a lower scale neural network, right? Now, because we have the identity mapping, your neural network will perform at least to that extent, right? Let's say you had a 50-layer neural network and a 100-layer. Your 100-layer is guaranteed, almost guaranteed, to work as good as your 50-layer neural network, because we have this identity added to it. We have this residual connection added to it. And that really, it seems so simple, right? And that's the beauty of it, right? It's like in a lot of machine learning problems, especially in computer vision, it's these very simple ideas that lead us across, the finish line, so to say. And specifically in the ResNet's case, this was the fundamental idea of next slide, of ResNet, is that you add this residual block to it. Another thing that we want to sort of give you guys an explanation is that while ResNet didn't, the ResNet authors didn't discover batch normalization and invent the method of batch normalization, they did popularize it, because it's in the ResNet paper that they really introduced batch normalization, the value it has in neural networks to improve the efficiency and the training time of neural networks, right? So what is batch normalization? Well, batch normalization, what you do is effectively, let's say you have a linear layer, right? You take the activations of your linear layer, and over the batch dimension, you normalize the activations, right? So what you have one go through of your linear layer, and over the batch dimension, for example, if you have 32 batch size, you take all those batches and you normalize each layer so that the activations of those layers with respect to the batch dimension, right? Not with respect to the layer. That's a very different thing. Have a zero mean and a unit 1 variance. And what this specifically does one of the benefits of this is it helps with gradient explosion, right? Because it helps your activation stay within a certain range. And the gradient explosion problem is sort of the reverse of the vanishing gradient problem, where your gradients might actually, if as you're backpropagating through your neural network, if the values of your gradients are greater than one, and your neural network is a certain size, they might actually explode as you go back. And so it's sort of like an antonym of gradient, a vanishing gradient problem, but batch normalization helps to solve this. And just a side note on that, if you guys were wondering, right, what the norm, as Jordan was explaining AlexNet, what that specific norm part of the AlexNet was, it's sort of very similar to batch normalization, but it's with regards to the features themselves, to the activations of the neural network. It's sort of like it's very similar to batch normalization, while batch normalization normalizes across the batch dimension. This norm normalizes across your neurons. So what it does is, suppose, for example, you have 10 neurons, right? And they each have activations. It normalizes the output of those neurons so that the neuron, which has, which effectively relative to the others is fires the most, that neuron is effectively increased. The activation of that neuron is increased relative to the others. So that's across your features, across your activations, while this is across your batches. And we later learned through ResNet and so on that batch normalization is better than that type of normalization. So, so just so that you guys don't confuse those two, they're very different.
And also one more thing is you may be like, okay, when I'm training my neural network, it's like, I'm passing a batch that's 128 or 256, right? Like, that's enough for you to get like a pretty good sort of batch normalization value for each layer. But what if I'm testing my network? Do I have to then pass in images from different classes and like make sure that, I'm passing at least 64 images at a time to classify? That seems counterintuitive. I want to just be able to pass in one image and be able to make my network work. Now, this is where batch normalization is very clever, because during training, your E of x, which is just the mean of your x across your batch dimension, and your variance of x are calculated based on the thing you have passed in. However, while that's happening, your network is also keeping a moving average of what this mean and standard deviation is, right? Mean and variance is. So it keeps that in mind. And then when you eventually were to do inference, it basically says, instead of using the mean and standard deviation of your input images, it uses this moving average results to be like, I think the data set has a general mean and standard deviation I think this data set has a general mean and standard deviation for each layer that's like this, and then you use that instead. So it is kind of like training what the E of x and var of x should be, but you're just doing a moving average as you kind of pass in a bunch of images while you're training. And the important reason for doing this is because, as you're training your network, that E of x and var of x, it's going to change because your input features are changing. So that's why you want to use, a moving average feature. And that's also why, if you were to look very carefully at your, applied track notebook code, whenever we do evaluation on the images, we do model.eval. That .eval tells batch norm layers in your model that, hey, we're in evaluation mode now. Don't stop collecting moving averages of mean and standard deviation. Freeze that, and when you pass an image, and use that instead. And when you do model.train, it says, okay, we're back to training now, right? We're back to training. Let's keep accumulating our moving average of mean and standard deviations. And before we move on to how ResNets are trained, I also want to quickly show you the ResNet paper. I also want to quickly show you what the full architecture looks like for a ResNet paper, because I think having that visualization is nice. So this is what the full network looks like for the paper. Very influential papers here, right? You can tell they went a lot deeper than at least AlexNet and also GoogLeNet, right? This was even smaller of a network than GoogLeNet. And, this was VGG19, which was a paper that was also published in 2014 that basically takes AlexNet and just makes it bigger. But basically, they're able to go less wide, so less number of channels. Like here, AlexNet has 512 channels, right? It can just use 128 channels and completely wipe out AlexNet, completely beat out AlexNet in terms of accuracy. And it's really, really deep. And it has this, residual connection. It just keeps jumping and jumping and jumping and jumping and jumping. And one quick thing is, as it downsamples in size, when that happens, instead of using a skip connection, because then your dimensionality doesn't match, it uses a 1-by-1 convolution to downsize everything. So yeah, and this is kind of what the architecture looks like. It's very simple to describe, but this did really well. Again, it beat out everyone else in the 2015 ImageNet competition. Okay, Liu.
Yep, it beat up, everyone with like flying colors, is what I was saying. And to give you guys a glimpse into how the ResNets were trained, one important thing that we want to emphasize is something called a learning rate scheduler. And they use a specific type of learning rate schedule where every time, as they were training, they took note of the error of their neural network, right? And every time the error plateaued, they decreased their factor of their learning rate by 10. And the reason behind this is, you guys remember last time when we were talking about how, in gradient descent, you're just trying to get at the bottom of that valley, right? You're just trying to get to the point where you have a minimal loss. But if you have a learning rate that's too high, you might just oscillate around that loss, never really reaching that minima. So effectively, as you go on, you have to decrease your learning rate so that you can sort of like get closer and closer and closer and closer to that minima, right? And the beautiful thing about this is, mathematically, we know that neural networks within certain constraints, there's something called the universal approximation theorem, that we know that within certain constraints, these neural networks should converge to any function, right? We know this for sure. We can't say surely for the world because there are a lot of complexities with worldly data, but we know for sure that they can approximate any function, right? But this is, we have to look at the learning rate as well. They can approximate at every function, but the learning rate has to vary over time. If you have the same learning rate, it might not be possible, as you're sort of oscillating around that minimum. And we can see right here, it's actually really cool. I remember Jordan, telling me about this before. We can see around 10 iterations, the error plateaus, right? Then they decrease the learning rate by 10, by a factor of 10. So now it's 0.01, right? And again, we see a drastic increase in error. Then again, every time the error drops drastically, that's around the same time when they, effectively drop the learning rate by a factor of 10. And so that's one way you can do this. That's one way you can add. And if you guys are interested on how you can do this, I can show you guys some code and so on later. In PyTorch, this is super easy. All that you have to do is, you add something called the learning rate scheduler, and you can say per 5 epochs, drop the learning rate by a factor of 10 by any factor you want, or you can do it manually if the loss for a certain amount of time gets here and decrease it by a factor of 10. There are also other methods of doing this, atom optimizers and so on. They do this automatically by looking at how has the gradient changed for this neuron. So do we have to decrease the learning rate and so on? There are other methods, and we explain those other methods later on. Jordan, is it possible for me to share my screen? I want to show them.
Yeah, I can do that. Yeah.
ResNet
Oh yeah, and right before Liu starts off with this explanation, I also want to mention one quick thing is, why do we do this learning rate drop, right? Why don't we smoothly decrease the learning rate? Why are we doing this drastic drop of learning rate? The reason is because what we want to do when we're using stochastic gradient descent is if we want to train a network that does well on both the training set and testing set, aka is able to generalize well. If you would imagine back to the loss landscape, we want to find a loss landscape that is very flat. Specifically, we want to get to a minimum that is very flat, that looks like this, instead of something that drops down really sharply and then back up again. Because a sharp minima is indicating that if you just change your input image a little bit, if you change your network parameters a little bit, you change some sort of input condition a little bit, it will drastically affect your loss. And we don't want that. We want the network to be very robust. By starting out with the 0.1 learning rate, which is actually really big, right? Like a lot of the other optimizers start with like 0.01 stuff like that. By starting out with a huge learning rate like this, basically what your network does is it never gets to a minimum. It kind of just jumps around really aggressively. It just kind of keeps teleporting around your lost landscape. And by doing this a bunch of iterations, your network will start to go towards a location that has a very flat minima or contains a very flat minima because as you jump around, you are not able to escape that flat minima really easily. So basically, after say in this case like 10,000 something iterations, we go, okay, I've jumped around so many times, right? I've jumped around so many times. Where I am right now should be roughly where that good flat minima should be. So I drop my learning rate and I do the same thing, but just on a smaller scale, right? Now we have kind of honed down our search. We do a really wide search in the beginning and we kind of hone down our search by using a much smaller learning rate. We keep doing that. And then as that plateaus, we go, okay, let's do that again. We divide our learning rate by 10 again, and we do that search, but just sort of at a very small scale. So you can kind of think of it as like, say like you're trying to find, where someone is, right? You want to start by searching, say, which country are they in, right? You look through all the country, you look at a really huge scale. Then you go smaller. You go, okay, then now I found the general area of which country they're in. It's still a pretty large area. Then you go to, say, the city within the country. That's dropping your learning rate by 1. You're looking at a much smaller scale, but you're pretty sure that on this large scale, you have found the correct-ish location. And you kind of go smaller and smaller. You go to city and you go to street. That's the intuition that's behind the sort of dropping learning rates, if that makes any sense. Okay, I'll hand it back to you.
Thank you, Jordan. So let me go and give you guys a glimpse. This is one of my assignments for 188, and I thought it would be a good example now. And in this, if you guys are interested, you actually make residual, you actually make a ResNet, like the actual version. Training millions of parameters on Colab is kind of crazy. But yeah, this is an example, right? So we have our residual block, and remember the previous diagram Jordan was showing from the paper. We have a residual block, a 3x3 convolution, 64, yeah, 64 times, and then we have our identity function right here, where we take the input of our residual block and we add it to the output of the residual block, right? And specifically, what we do in this case is we take this is just a forward function for our block. We take our input and we branch out. One is the residual block, but we add our input back to the output of our residual block. So do you guys see where we're doing this? We take our inputs here. I'm putting inside a specific variable called z, and then after I go through the residual block, after I take my input, I put it through a convolutional layer. I take that output and I put it through a batch normalization layer. This is how we specifically initialize batch norm, and then we take that output, we put it through ReLU. Was that right? So sorry, there might be a little bit of an error there, but this is the gist of it, right? At the end, we take our residual block and then we add it to the output to the previous input that we had, and then that's it. We have our ResNet, and we just layer these ResNets together. And so, this specific example, it's ResNet 18. We make 4 layers of our residual blocks, and we just put those layers one after the other, after the other, after the other, after the other. And then that's all we have to do. It's as simple as that. You can create this ResNet, the ResNet 18 architecture, the ResNet 34, 50, if you want at home. It's super simple, super easy to do. And yeah, this is how we do it. And if you guys want to try this at home, if you want to actually import your own ResNet models, all that you have to do is you can go to Torch Vision. There's a Torch Vision.models as models, and you can import this ResNet model and you can try it for yourself. So it's again, it's kind of a beautiful thing. You can actually work with these large models in your convenience. So to go back to the slides, before that, does anyone have any questions before we go into zero-shot learning? Any questions at all? ResNet? You guys can put it in the chat. Sorry. Okay. through it. Okay. So zero-shot learning. Now we'll be talking about zero-shot learning with computer vision. I think you guys might have heard about this for large language models, right? GPT, for example, ChatGPT is a fine-tuned version of the GPT architecture, and it's fine-tuned so that it can perform zero-shot language model tests, right? So that you don't have to ask GPT a question 5 million times for it to get the right answer. It gives you the right answer at the first time. And that's what zero-shot effectively is. It's effectively saying, suppose we have a case that we haven't described in training time, can your model generalize to this case? So rather than working with known classes and classifying unseen data into known classes, now we're classifying unseen data to new classes, right? And this is a very big shift. And this kind of makes sense because that's effectively where we want to go from a machine learning point of view, right? Like as humans, I can see something that I haven't seen before and still classify it. I have that level of pattern recognition where I can say, oh, this might be a specific type of dog breed that I haven't seen, or this might be a fruit because it looks like a fruit, right? I can say those things without needing to go through thousands and thousands and thousands of versions of that or so on. And our model should be able to do that, right? This is the future of computer vision. So what's the problem, right? Currently, a lot of models, you look at ResNet, you look at AlexNet before that, and you look at multiple new computer vision architectures today, what they do is they effectively take your input image, and they're mapping it to a vector, right? To let's say you have 100 classes, you're mapping it to a 100 class vector. And all you're trying to do is you're trying to make one of those one part of the vector light up, sort of, right? So that the max of that vector is your classification, right? So let's say, for example, on your vector, the 50th index represents, let's say you're trying to map fruits, the 50th index represents bananas, right? If you input an image of a banana, you want that part of your vector to light up, right? You want that part of your vector to be activated more than the other vectors, right? So you're effectively just mapping it to a vector without that much information. And this is very hard to scale up because suppose you have, a million different things that you want to classify, right? It doesn't make sense to use these vectors to map your image to sort of the number of vectors that you want. And so the problem arises, right? You're mapping it to discrete representation. What if we map it to like a pseudo-continuous representation, like compared to this discrete representation that, we can have anything we want, anything in this world that we want, we can map it to that, right? And this is where, next slide, Jordan. Yep, thank you. And this is where the similarities with NLP comes in, right? So we haven't talked about this really yet, but we will talk about this. We will talk about this next theory track. Specifically, what I want to emphasize is something called embeddings, right? So for it's actually crazy. This is also similar with the original computer vision techniques, as Jordan was talking about, like sort of the bag of images that you had. Originally, for words, we represented the words as sort of like a one-hot encoded vector of the words. You just had your total vocabulary, and you had this vector of all zeros until the index of your word. That index was 1, and everything else was 0, right? Originally, that's how we represented images. But then we went from that representation to a word embedding representation, where word embeddings, they're effectively mapping your words, millions of words into a vector space, right? Where where if your vectors are close to each other, right, that means that they're more similar to each other from a semantic point of view, that they have similarities to each other. That's what word embeddings are doing. And we'll explain more of that in detail. I just wanted to give you guys a brief overview of word embeddings before, but we'll explain it next time because this is a very, very important concept. And as we can see right here, right, we have cat, kittens, dogs, houses, and we have man and woman. Man and woman, for example, they have a very similar word semantic relationship, right? And so in your embedding space, they're going to be similarly combined, right? So if you take the dot products, for example, if you normalize the vectors first and take the dot product, that dot product will be greater than, say, for example, man and cat, right? Because man and cat, they're not that similar. And you can have all these operations in these word embeddings that are very, very unique. What's the beauty of this is if you have a million words, you don't have to have a million dimensional vector. You can just have a few thousand dimensional vector. And this will accurately represent your dimension. So in many ways, it's actually even compressing, the issue for you. It's kind of beautiful, actually. And next slide. Right.
Lee, you're the one controlling the slides.
Oh, fuck. Sorry. I'm sorry, Jordan. Yeah, sorry. Image encoders. I'm so sorry. Image encoders. So specifically, we'll sort of go from this word embedding idea to images. How can we convert our word embeddings to images, right? So how can we sort of move from word embeddings to image? And before you start, I just want to emphasize that it's not as easy for images, because for images, compared to words have relationship with each other. Images, they don't necessarily have relationship with others unless you're dealing with videos, for example. So the image embeddings are a little bit difficult, right? But we have another very similar representation, and that's, we can just encode our image into a latent space representation. And just to give you guys a brief overview of what a latent space representation is. So suppose, for example, we take our input, right? And we have a neural network that takes our input, has a lot of different operations on it, and it maps it to a smaller dimensional tensor, and then it maps this tensor back into the reconstructed image. So all we're doing is we're taking our input, mapping it to a smaller dimensional representation, and then we just reconstruct that image, and we check if that image is close to our input image. So this effectively is a form of compression, right? We're compressing our image, seeing how far we can compress it, how far we can get the most important information from our image, and then we take our image and and then we decompress our image and we say, okay, this is good. We've compressed our image to this size tensor, right? And that's the beauty. That's what machine learning scientists are doing. They take our image, and I'll explain why this is important. They take our image encoding, which is kind of like our image embedding, right? They take that image embedding, that latent space representation, they take our textual representation, and they mix them together. And then we get a classification algorithm. And I'll explain what that specifically is, right? Specifically, multiple different organizations do this, but one organization that does this really, really well is OpenAI, right? OpenAI's CLIP model is revolutionary. It is just simply remarkable. Today, it might not seem as though today, but honestly, I'm almost certain that this is the direction that computer vision is going to be taking, because it just makes a lot of sense, right? What they do is they take, they have this very large data set of captioned image pairs, right? They have this very large data set of captioned image pairs. And how they train their model is they train their model to output a similarity score, rather than just saying this image and rather than giving it an image and saying match it to the caption, they give both the image and the caption, right? And then they output a similarity score. So what this does is it effectively leads to a mixing of the embedding space of your text and your images, right? So this is kind of a multimodal model that has image and textual capabilities, right? And if you guys are wondering how they do this, just to give you guys an analog of this, is not how they do it, but just to give you guys an analog of this, right? Have you guys, I know we're not in person, so maybe it's a little bit hard, to give you guys a demonstration on the Blackboard. But if you guys know what the dot product is, right? Think about your image and your text encoders releasing vectors that are on a similar vector space, right? We take those two vector space and we take the dot product of those vectors, right? The key thing here is that those vectors are normalized. So they're normalized. So if you take the dot product, one of the vectors isn't too large, it's not going to be meaningless. There's a meaning to their dot product in this case. And whichever dot product is the largest, right, that similarity is also large, meaning the similarity between your text encoding and image encoding is high, right? But if that dot product is small relative to others, then that similarity is low. So rather than training it, you get an image and we output a caption, we're training it on the similarity between those. So it just releases a similarity. So that's how the OpenAI model trains it. And you guys might be wondering, how does this generalize, right? How does this work for unseen classes? Well, the beauty is that there are embeddings for effectively every single word, in a language, right? Every single English word has an embedding for it, right? So if we want to generalize our machine learning model to see unseen classes, all we have to do is we have to, given an image, we say, for example, if it's a cat and dog image, and if our machine learning model has never seen cats and dogs, we give it a text that says, okay, this is a photo of a cat and a photo of a dog, right? We run the clip model with the image that we're in question. We don't even know what it is. And the clip model says, this is most similar to the cat image. This is most similar to the dog image. In this case, this is a photo of a dog. And we just take the max of those two. And it might be an image of a dog, it might be an image of a cat. And this is beautiful because we can extend this to any single word we want. Not saying it's going to be effective for all those words, but we can extend it, right? And the crazy thing is it works. It's as good as ResNet and even more on some benchmarks. So it's working like in an amazing way. It's working in a very beautiful way. So yeah, this is just an example of where computer vision might be moving. Do you guys have any questions on this? Okay, good. Go to the next slide. So some motivations for RNNs. There's type for that. So now we're going to get to RNNs, which are recurrent neural networks. This is sort of the motivation for transformers, long-term, short-term memory, and so on. We'll learn what those are after this, but this is sort of the pretense of those things. And it's very important for another type of machine learning task, right? So what have we done so far? So far, we've had models that work in a feed-forward manner. We give them an input. They give you an output. That data is non-sequential, right? And it's static, and it's dependent, and the input space is dependent on other elements, right? For an image, it's just as simple as you give it an image, it outputs something. There is no level of complexity to it, right? It's not dependent on any other input. Let's say you have an image with a bunch of dogs and cats. One image is not dependent on the other image. You just give it an image, output something, you train it, that's it, right? But a lot of data in the world isn't like that. Say, for example, stock market data. Stock market data is dependent on the previous data. So you might have, yearly data, monthly data, per minute data, per second data, per millisecond data if you're in high frequency trading. All the millisecond before, the second before, the year before is important. So you have to take that data into account, right? So what do we do when we need to take that data into account? What do we do when we need some type of memory? And that's where recurrent neural networks come in. That's the beauty of recurrent neural networks, right? And this is an example, of a video where every single frame in that video has a relationship to the other. If you want to understand where you're in while you're watching a movie, you have to understand where you were before. So there's sort of this idea of time steps, which is crucial to understanding where recurrent neural networks are. And we already explained why sequences are important, but just to give you guys an overview of some sequential data. Audio is one sequential data. If you guys want music, for example, if you want to generate music or you want to analyze music, you need to understand the previous sequences in your music. Textual data, GPT, like for example, Siri, right? Siri is an RNN. If you guys are interested, the architecture of a Siri of Siri is an RNN neural network, and yeah, it's pretty cool that now you know what Siri is based on. Even videos to a certain extent are sequential data. Even though RNNs for video doesn't really make sense, it's very time consuming. And so just to get into a few concepts of how RNNs work, and we already explained, how RNNs used. Before, like I said before, we had an input, a hidden layer, and an output. That's all. We didn't take into account our other inputs, our other training instances, we only care about this one. Now, though, we have an input, we have a previous hidden output, and now we have the hidden output of this time instance too. So I want you guys to shift your understanding now from sort of a static machine learning framework to a more time-dependent machine learning framework. When we're working over time steps, right? Suppose you have n time steps, for example. If you're on time step k, for example, your previous hidden is the output of your hidden layer at time step k minus 1. So you go one time step before to get to where you are now. And so we take that previous hidden output into account. And so this is an example of a recurrent neural network, right? So we have an input, and this is over time step t and t plus 1. So we have an input, right? We take that input and we output something. Your neural network outputs something, and then after we output something, we take the previous hidden output, we transform it in some way, and then we feed it back in to your new input. So for example, suppose you have, for example, the fox jumped over the fence. Like you guys know that the quick brown fox jumped over the fence. We would first input we would get an output. Then we input, then we would take the previous, we would take the previous hidden output of the word the, and we would input it into the next time step, right? Where we're saying the quick. Now we're gonna sort of keep that information with it, and this way we have memory, because we're looking at all the past words, the words that we had before, so we can take those into account while making new decisions. And so that's effectively what recurrent neural networks are, and that's why they're called recurrent. You guys ever study computer science, you guys know why we call it recurrent is because we're sort of looping back in time every step. It's like we're calling the neural network again and again and again and again with the previous hidden output that you had, right? And so that's where the recurrence aspect comes in. And yep, this is just another example of a recurrent neural network. You have your input, you transform it in a linear layer, for example, then you have your output, and then you take your previous hidden output, you put it through a transformation, and you put it back in. You feed it back in to your neural network, right? And so it's kept in the loop of your neural network. And over time, you can unfold this neural network, and we'll explain what the unfolding is. This is very tricky. Like a lot of people, when they think unfolding a neural network, they think about literally unfolding your neural network, but that's not what we mean. And we'll explain. It's more unfolding it over time. Your neural network stays the same, but the values of your neural network change over your time steps, right? Let's say you have t time steps, the values of your neural networks change over your time step. So that's what we mean by unfolding it, right? It's the same neural network, it just different over different time steps. And you guys might be wondering, how does backpropagation work for this? How do we train it actually, right? And the way we train it, we use backpropagation, but we use a variant of backpropagation called backpropagation through time. So we treat every single time step as a layer, right? Rather than, sort of the alternative method, which is very computationally intensive, we treat every single previous time step as a layer to the new time step, right? And so that's how we backpropagate through our neural network, and this is called backpropagating through time, and that's what we mean when we say unrolling. We're just unrolling your neural network through time. It's the same layers, it's the same neural network, but every single time step is treated as an architecture. And when you think about it, that makes sense, right? You sort of transform this very complicated problem of, having to deal with those recurrent connections into a much simpler problem, just having your previous time steps as layers to your next time step, and we just have gradient descent for that. That's what we mean when we say we're unrolling. And surprisingly, this technique, backpropagation through time, isn't only useful in RNNs. It's useful for any time you have a neural network that has some sort of like time dependency to it, right? For example, if your neurons fire at a certain rate across time, you're going to use backpropagation through time because you need to sort of have that time information accounted for. And so yeah, this is a very powerful technique that we use. Sorry, let me go back. The pros and cons of RNNs. Some advantages and drawbacks of RNNs, right? One big advantage of RNNs is you can potentially have processing, you can process inputs of any length, right? RNNs give you that capability. Even if you have 100 words, 1,000 words, and so on, you can still process that length. No one said anything about the efficiency. The efficiency might not be there, but you can do it. And model size does not increase with the size of the input. Computation takes into account historical information. This is what we're talking about specifically with the memory. Your neural network, your recurrent neural network has memory because it takes into account the hidden outputs before. And also weights are shared across time. So you don't actually have to have new weights for your every time you run your recurrent neural network, right? You don't have to have new weights. But there are a few drawbacks. One is that you have a vanishing gradient problem. Especially as you unroll your recurrent neural network over time, you have the issue of vanishing gradients, right? Because this recurrent neural network goes deeper and deeper and deeper and deeper and deeper and deeper and deeper. And as you guys, as we talked about before, you have the issue with chain neural as you're multiplying those gradients, over your neural network, and you're going back into previous layers. Your gradients get smaller and smaller and smaller and smaller and smaller. So previous words have less of an impact on the words now. And that becomes an issue because you're not really getting the semantic relationships that you want between your word, or a better term, you're not really taking into account the words that you had before and how they affect the words that you have now. Additionally, it's very computationally expensive, right? It's very slow. One reason is it's just very slow to run, right? If you have a recurrent connection, that takes quite an amount of time to run. But not only that, is backpropagation through time also takes a long time to finish, right? It takes a long time to perform gradient descent in this case, because you have to unroll your neural network. So you're not only working with the state of your neural network now, you're working with the state of your neural network at t-1, t-2, t-3, t-4, t-5. It can go on endlessly, and this is very, very computationally intensive. And so it doesn't make sense to, do this as much now. Additionally, can't consider any future input for the current state. That's also one drawback. So yeah, and just to give you guys, a sense, we're working with this. We worked with this back many years before. Right now, we don't really use RNNs as much, but a lot of the fundamental ideas that came from RNNs, we still do use them, right? For example, LSTMs, we still use them in some areas, and backpropagation through time, which came as a result of RNNs, we still use for example, spiking neural networks. We use backpropagation through time for spiking neural networks and so on. So a lot of the fundamental ideas of RNNs come into play later on. So yeah, and thank you guys for coming. We appreciate it. We hope you guys had a good time. The feedback form is right here. Yeah,
everyone's right over there. The attendance code, you can use the members of acm.com with the code going deep. And next week, we're going to talk about embeddings, LSTMs, transforms, and an introduction to large language models. So this is going to be a really exciting one, because if you are into natural language processing, this is going to be the workshop for you. And we're going to have our team, who is kind of our resident LM expert here at ACM AI, come and explain what all these really mean. So hope to see you next week. We will be in person next week, thankfully enough, unless the same storm hits twice. But yeah, thanks for coming, and we'll see you next week.